Capacitor and capacitance. Most electronic devices, such as radios, computers, and MP3 players, make use of components called capacitors. Capacitors are used to store energy in electrical and electronic circuits. This means that they have many available applications, including smoothing varying direct currents, electronic timing circuits, and powering the memory to store information in calculators when they are switched off. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. A capacitor is an electrical component that possesses the ability to store energy in the form of an electric charge on two separated metallic plates. A simple capacitor consists of two electrical conductors that are separated by a distance. The symbol for a capacitor, as shown in figure, will reflect this. The space between the conductors may be filled by vacuum or with an insulating material known as a dielectric. To move charge onto the plates of a capacitor, it must be connected to a voltage supply. When the plates are connected to a battery, there is a brief current as of the voltage supply draws electrons from one plate and deposits them on the other plate. The negative terminal of the supply pushes electrons onto one plate, making it negatively charged. Electrons are repelled from the other plate, making it positively charged. The current tries to flow through the capacitor from its positive plate to its negative plate, but it is unable to flow due to the separation of this with an insulating material. This leaves the first plate with charge plus Q and the second with charge minus Q. So each plate gains an equal and opposite charge due to the conservation of charge. The current stops when the potential difference across the capacitor is equal to the electromotive force of the supply. We then say that the capacitor is fully charged. The voltage supply does work in separating the charges. Since the two plates now store equal and opposite charges, the total charge on the capacitor is zero. When we talk about the charge stored by a capacitor, we mean the quantity Q, the magnitude of the charge stored on each plate. The ratio of the charge stored to the potential difference between the plates is defined to be the capacitance of the capacitor. The greater the capacitance, the greater is the charge on the capacitor plates for a given potential difference across it. The unit of capacitance is the coulomb per volt, or farad F. A 22 microfarad capacitor is charged by using a constant current of 2.5 microamps to a PD of 12 volts. Calculate the charge stored on the capacitor at 12 volts, the time taken. We are given the capacitance and potential difference. We use the capacitance formula. So capacitance times voltage gives stored charge. The electric current is charge divided by time. So the time taken is charge divided by electric current. The capacitance of a device depends on the geometrical arrangement of the conductors. The capacitance of a parallel plate capacitor can be calculated from three facts. Distance. The further apart the two plates are, the less the free electrons on the far plate feel the push of the electrons that you are adding to the negative plate. making it harder to add more negative charge to the negative plate. This means that the capacitance of a parallel plate must be inversely related to the plate separation. Mathematically, it's given as follows. Area. By increasing the area of the plates, we can put more charge on the plates before the repulsive forces become a problem. Larger the plate area, more is the capacitance value. Therefore, the capacitance is proportional to the overlapping surface area of the plates. Mathematically, it's given as follows. The effect of dielectric on capacitance is expressed by a constant called the permittivity. The greater the permittivity of the dielectric, the greater the capacitance. Likewise, lesser the permittivity of the dielectric, the lesser is the capacitance. These three factors which affect the capacitance of a parallel plate capacitor can be expressed as the parallel plate capacitor formula as follows. In a laboratory experiment, two parallel plates, each of area 100 cm squared, are separated by 1.5 cm in a vacuum. Find its capacitance. How much charge is on the positive plate if the capacitor is connected to a 3 volts battery? Substitute the values given into the formula. Do not forget to convert the centimeter units to meters. Charge is capacitance times potential difference. When a capacitor is charged, electrons from one plate repel electrons from the other plate, which then move to the positive terminal of the supply. Work must be done by the power supply to deposit negatively charged electrons onto the negative plate, as like charges repel according to Coulomb's law. In order to charge a capacitor, work must be done to push electrons onto one plate and off the other. Look at the figure. The voltage applied to charge the capacitor is measured with a voltmeter, and charge accumulated is measured by removing the charged capacitor from the circuit and connecting it to a Coulomb meter. The graph shows the charge stored on a capacitor plate against the potential difference over the device. The potential difference V is the energy per unit of charge stored on the capacitor, and Q is the charge. So the product of these two quantities is the energy stored, and this quantity is equal to the area under the graph. The work done in charging a capacitor to a particular potential difference is given as follows. This equation can be combined with the equation for capacitance to give two alternative equations for energy stored. Pay attention. Calculate the energy that can be stored on a 5000 microfarad capacitor that is charged to a potential difference of 25 volts. We are given the capacitance and the voltage, so we take the second formula and replace the capacitance with 5000 microfarad and voltage with 25 volts. A further way to modify capacitance values is to combine two or more capacitors together in much the same way that resistors. Multiple connections of capacitors act as a single equivalent capacitor. The total capacitance of this equivalent single capacitor depends on how they are connected. There are two simple and common types of connections, called series and parallel. Capacitors in series store the same amount of charge Q because of the same current charges both capacitors. The potential difference across the capacitors must add up to give the electromotive force of the cell, V. The source of potential difference, V, is equal to V1 plus V2. Using the definition of capacitance, we get the total capacitance of the series combination. In series, the reciprocal of the total capacitance is equal to the sum of the reciprocals of each capacitance. In a similar way to the case of capacitors connected in series, we can consider two or more capacitors connected in parallel. Parallel capacitors have the same potential difference across them when connected as in figure because both are connected to a source of potential difference V, and this is the common potential difference across both capacitors. Charge is conserved, so the total charge stored on the combination is equal to the sum of the charges on each capacitor. Substituting for Q from the definition of capacitance gives. So the total capacitance is given by the formula. When two capacitors are connected in parallel, the total capacitance is equal to the sum of the capacitances. Find the equivalent capacitance of each capacitor in figure. In series, the reciprocal of the total capacitance is equal to the sum of the reciprocals of each capacitance. When two capacitors are connected in parallel, the total capacitance is equal to the sum of the capacitances.